Hello, welcome to the pre-class video assignment for section 1.9. This is a little bit an extension of the previous section 1.8. So it is very much related to section 1.8, exact equations. It is basically a method whereby we can kind of potentially have a shot at still solving exact equations, or I should say, still solving differential forms of differential equations that are not quite exact. There's a chance that we can make them exact and solve them anyway. So there's a little illustration on the first page of this handout that we're going to look at in this video, and we will cover the rest of it in class together. So this should be a little bit shorter than most. Again, when DEs in differential form are not quite exact, not all is necessarily lost. Sometimes we might be able to find a special factor that we can multiply through in order to make it exact. Somewhat inconveniently, this is also called an integrating factor often. But it's a little bit different from the integrating factor we use to solve linear. But anyway, we're going to run through a little example here, a demonstration that something that might not be exact initially, we might be able to make it exact and solve it anyway. So this is our initial DE in differential form we're going to attempt to solve. So if we look at this equation, our first step in section 1.8 was to always verify if we have an exact DE or not. So if we do that here, this is our M function, this is our N function. And if we do our little trick, so we take the M function and do partial differentiation with respect to y, we get 2y plus 2x. If we take the n function, minus x squared, do partial differentiation with respect to x, we get negative 2x, and clearly this is non-exact. These are not the same function, and this is not exact. They are not wildly different, but they are not exact. So here's sort of our little demonstration of what's coming up in this section. Let's suppose we take our non-exact DE and multiply it on both sides by this special function. Again, where this function comes from and how you determine what this might be, that's kind of the topic of the section that we will work through together. But let's suppose we were magically given this particular function here, and we then multiply it through the original differential form DE. So we multiply through by y to the power of minus 2. Simplifying a little bit, this becomes my new m, right? Y minus 2 times y squared is 1. Y to the minus 2 times 2xy is 2x over y, and then this one is a bit more straightforward. We get minus x squared over y squared. So now we have this new m, this new n, and we can now check whether this is exact. And if you check it out, again, differentiate the m with respect to y, we get negative 2xy to the minus 2. And similarly, if you do the derivative of n with respect to x, we also get negative 2x over y squared, or y to negative 2x times y to the minus 2. So this is now an exact DE. That is meant to say now, not non. That is a now. All right, if this DE is now exact, then we can solve it, yes, by our methods from section 1.8. So one method is to take the M function and then let us partially integrate with respect to x, because again, the M function, if this is exact, the M function is the partial derivative with respect to x of this function f of xy that we're trying to find. So let us do a partial integral with respect to x. So if we partially integrate 1, you get x. If we partially integrate 2xy to the minus 1, we would get x squared y to the minus 1. And again, there's a constant generated because we are integrating with respect to x. This constant could have been any function of y. So then the trick is we take that, this is basically our representation of our f of xy function. We then differentiate it partially with respect to y. So the x will go away. then partially integrate this with respect to y, we get negative y squared over x squared over y squared, and then g prime of y. So if this is correct, again, the idea would be that we had, just let me write this over here. This is the idea from 1.8, but just as a reminder, if we have an f of xy function and we have our function m, which is the partial derivative with respect to x, and we have the n function, which is the partial derivative with respect to y, what we're really doing is we're starting here with m, we anti-differentiate to get a representation for f of xy, then we do a partial derivative to get f sub y, and so whatever we get over here, this should be our n. Excuse me, not that. This should be our n, right? This is our partial derivative with respect to y. This should be our n. So if we compare these two things, I have minus x squared over y squared, minus x squared over y squared, and then I've got g prime of y, but there is no other function of y here. Therefore, g prime of y was 0. Therefore, the antiderivative of g prime of y was actually just a constant, which is as simple as that gets. So then we know that this is a representation of f of xy, and we know from previous work that we take that and set it equal to a constant. Naturally, the C1, there's no point in having an unknown C1 and an unknown C2, so we just add them together, put them on the right-hand side, and this is our solution function. In implicit form, as we often find here. So that is all good. That is our solution. Now you might ask, we actually changed our original DE when we multiplied through by this function. So how do we know that this is well, we found a solution to this new DE. How do we know that it's also a solution to the original DE? And it turns out that it is. And again, without proof, but we can easily check this. So if we take our potential solution and check it in our original DE, let's see what happens. So if we take our original function here, our original solution, and differentiate it implicitly, we get a derivative with respect to x of x is 1. Derivative of this with respect to x is 2xy to the minus 1. This is a product rule, of course. So the first one, derivative of the first, 2x times the second the way that it is. And then we get the first one, 2x times the derivative of y to the minus 1, which is minus y to the minus 2, hence the minus and x squared over y squared. So this is what we get from implicit differentiation. If you work on this a little bit and convert it to differential form, you do indeed get the original question that we had here. This does in fact work to solve the original DE. So this is our little trick. All right, so this is just a demonstration of what we are looking for. And it is no small feat. So, but the point of the rest of this section is, where does this guy come from? Where do we come up with this magical integrating factor that actually is the right thing to turn our non-exact DE into an exact DE that we can solve and give us a solution to the original? That is not a trivial question and takes some thinking and explaining. So that is something we will deal together with in class. But given this guy, the method is, again, hopefully fairly clear. So the only thing left then is I do have a very similar example like the one we just talked about here. I've got a very similar example for you to work through in My Open Math, and you will be, the question is scaffolded so that you are going to step through the process for one example, and that will be it for your pre-class video assignment for this section. So thank you, and we will see you in class for the rest of it.